You are on the live screen.
A very good evening to everyone present here. It's my pleasure to welcome you all to this 20th lecture of the International Virtual Workshop on Global Seismology and Tectonics. This morning, we had a very nice interactive session with Professor Kalachan Sain, Director, Wadia Institute of Himalayan Geology, Dehradun, India. In all those past lectures, we have heard about the diverse topics on seismology and earthquake from various renowned personalities across the globe. Today in this session, we are going to hear a related but a slightly different topic which will be delivered by Professor Joachim Gottsmann from University of Bristol, UK. He will deliver his talk on the new insights on the inner workings of volcanoes. On behalf of the entire organizing team, sir, I welcome you, Professor Grossman. And before we proceed, may I request our session chairman, Professor J.R. Kyle, sir, for his initial remarks. Over to Professor Kyle, sir.
Thank you so much, Chinmay. Good evening to Professor Gottsmann. We warmly, very heartily and warmly welcome you to this session. We are all looking forward to listening to your lecture on volcanics. Actually, we have not, so far I think this would be a new topic for all of us. And we look forward to learn something from you, from your vast experience and knowledge. Thank you so much for kindly accepting our humble request to accept our invitation. Thank you so much. Over to Chinmay, please.
Thank you, sir. So now I'm going to introduce our today's speaker briefly to our participants. Professor Gottsmann has completed his MSc from Friedrich Alexander University, Erlangen, Germany, and PhD from Ludwig Maximilians University, Munich. Currently, he is serving as a professor at School of Art Science, University of Bristol, UK. Professor Gottsmann, his research interest includes investigation of processes relating to fluid and magma migration, modeling of the subsurface dynamic processes, quantification of physicochemical properties of silicate melts, interaction between melt rheology and eruptive processes, etc. He is the recipient of many fellowships and awards like Marie Curie Individual Fellowship, Royal Society University Research Fellowship, Weiser Medal, etc., and also serving as an editor and editorial board member of many reputed journals like Physics and Chemistry of Art, Journal of Volcanology and Geothermal Research, etc. He has published more than 250 research articles in journals of national and international repute. Now, may I request our today's speaker, Professor Joachim Gottsmann, to take this digital forum and enlighten us with his lecture. Over to you, Professor.
Okay, thank you very much. Thank you very much for the kind words, and let me express my gratitude for being able to speak at this esteemed conference, and looking forward to giving you a talk on a topic that is perhaps not overly familiar with you, but hopefully I can convey some of the interesting new findings on how volcanoes work in this presentation. Now, I've tried to keep things as simple as possible. I'm trying to avoid, terminology that really only volcanologists can understand, and I'm trying to make this entire issue accessible to a large and diverse audience. So hopefully I will succeed in this endeavor. Let me again thank you for accepting my presentation for this conference, and I'm looking forward to deliver this talk and hopefully also be bombarded with quite a number of questions at the end of this talk. I'm more than happy to field any questions you might have. Okay, so if it's okay, I would now switch the screen and start the presentation. Yeah. So I'm going to be sharing my screen here. So, right. Can you all see my screen?
Yes.
Okay. Fantastic. So I'm going to start by showing you this this slide here. Now, obviously, the title of my talk has already been introduced. It's new insights into the inner workings of volcanoes. And this is a picture of me standing on a volcano in Bolivia in South America at more than 6,000 meter elevation, conducting some field work. In this case, this is a GPS sensor. And why we've been working in this area, I'm going to tell you in a minute. But that, you know, it's a beautiful scenery, and it kind of shows you the kind of research that I'm undertaking. I'm a geologist by training, but over the last more than 20 years, I've really been working in volcano geophysics, and mostly in the broad field of volcano geodesy. So GPS and gravity, gravitational measurements or gravity surveys are my tool. So I'm someone who spends a lot of time in the field, and also both educating and teaching students on field methods, but also undertaking quite substantial field trips in order to gather data in various parts of the world. I'd like to acknowledge the sponsors over the last probably by about 10 years or 15 years, the NSF in America, with collaborators being based in the US. The funding agencies here in the UK that I'm mostly sort of being supported by is NERC, it's a Natural Environmental Research Council, and a lot of the research that I'm going to be presenting today has also received funding from the European Commission. So I'm really grateful for their continuing support in providing funding and grants for conducting the research. This is a really brief outline here of what I'm going to be talking about. I'm going to give you a bit of an introduction on the issue of volcanic unrest. I'm not entirely sure whether you know what volcanic unrest is all about and its significance and so forth. And I really want to introduce a couple of underpinning processes behind volcanic unrest. And those processes are exemplified by a couple of case examples here. Number one is what I would call a zombie volcano, and I'm going to explain what I mean by a zombie volcano straight away. Again, we're going to be traveling to South America and Bolivia to a volcano called Uchuruncu. The next part of the lecture is on issues to do with protracted unrest. What do I mean by that? Well, it's unrest that's really occurring over a long time scale and not necessarily culminating in a volcanic eruption. I'm going to be presenting the case study here from the main Ethiopian rift in a volcano called Betty. Last but not least, we're going to be talking about volcano tectonic linkages, because both systems, seismic systems, tectonic systems, and magmatic systems are intimately linked. It's very easy to find out if you compare a map of the global distribution, or showing a global distribution of volcanoes and global distribution of earthquake epicenters, you see a one-to-one correspondence. So in other words, tectonic systems and magmatic systems are very intimately linked. And I'm trying to give you two examples from El Salvador in Central America and also in Turkey to showcase the link between such systems. And finally, I'm going to be ending in about 45 minutes time with a brief summary and an outlook and implications of the research that we've been undertaking over the last 10 to 15 years on these volcanoes. So without further ado, I'm going to go straight into the introduction here of a volcanic eruption. And this is really the one and only picture I'm going to be showing you of an eruption. I mean, they are awe-inspiring. Anyone who's ever witnessed a volcanic eruption will be reminded about this event for their entire lifetime. This is a volcanic eruption that occurred a couple of years ago in South America. Cordon-Cauye, it's called, in Chile. And the reason I'm showing this is actually because this is a volcano that really hasn't been very active in a long, long time. But it almost erupted out of the blue. And this provides a challenge, really, because with volcanoes that show long period of what we would call inactivity, or actually dormancy, it's really hard to identify the subsurface processes that give rise to a renewal of volcanic activity. And what my talk is really concerned about is not about what's going on in here and the eruption column and the eruption processes there that shift magma to the surface, but what I'm really interested in is stuff that occurs beneath those volcanoes prior to an eruption. In other words, these are the processes that can be described as pre-eruptive, although we are never, unless there is an eruption, you're never really sure whether the processes that you're studying are indeed pre-eruptive or whether it's just part of the normal non-eruptive lifetime of a magmatic system. Now, it's interesting to see volcanism in a slightly different context. I mean, if many of you will have studied geodynamics and magmatic processes in the undergrad studies or postgraduate studies, and it's not really a surprise, but most of you will have heard that probably about more than 90% of all magmatic events don't make it into a volcanic eruption. So in 9 out of 10 cases where magma is produced in the crust or the mantle, it stays there. Maybe it travels, a few kilometers, a few hundreds of meters, but then it's getting arrested and it actually contributes to thickening the crust and building the crust. But really, out of 10 occasions, only one magma ascent will actually make it to the surface to create a volcanic eruption. So one way of looking at volcanic eruptions is really that they are sort of an accident within the Earth's crust. Something goes wrong, and the stuff that goes wrong permits magma to rise to the surface and erupt. Now, there's different concepts. No one really knows what the magma reservoir looks like, an active one, because we can't drill into them. We don't really have a good idea of what they look like. What we need to use is geophysics or petrology or geochemical studies in order to help constrain what we think these magmatic systems look like. And very often we're presented with cartoons such as those. I'm sure you've seen such cartoons in the past. Some of them are more simple than others. Others are more complex than others. But this is a very simple one. And for a long time, a magmatic system has been sort of envisaged as some sort of a vat, a void in the crust that is filled with liquid rock called magma. And somehow this magma chamber here is being replenished by a deeper reservoir. So that's a very simplistic view of the system, but it's still pretty much entertained throughout the sciences. I tend to think about the last 10 years or so, there's been a bit of a paradigm shift in how we envisage these systems. And what has really emerged over the years is something that is called a trans-crustal system, whereby if you look at the petrological fingerprint and geophysical fingerprint, you might actually find that the volcanoes that erupt magmas, that many of these magmas have very distinct fingerprints, and you have contributions from different magma chambers throughout a vertically extensive magma plumbing system involved in these eruptions. So you're tabbing a little bit of that, a little bit of this, and a little bit of that, and that's all gets mingled up and then erupted at the surface. So this is a drastically different view or sketch of the conceptual model behind the underpinnings of volcanic eruptions compared to this one here. And really what I'm going to show during this talk is that most of the findings that we have made in various parts of the world in recent times are much more aligned to sort of this paradigm of transcrustal systems rather than some sort of an isolated magma-filled vat at some part or some storage depth within the crust. Okay, so this is really perhaps a concept to bear in mind. If there's one takeaway message here from this slide, is that bear in mind that we think we have sufficient evidence from all sorts of different investigations that many magmatic systems are really transcrustal, and they connect the surface through the entire crust to the mantle. Okay. The concept there is really that you have some sort of a mantle contribution where magma is being generated or melt is being segregated and then moves up towards the surface, but it's being stored at different depths before it's then eventually erupted. But be reminded that, of course, most of the processes behind magmatic generation and so forth, they occur at depth and they also stay at depth. It's only, as I said earlier, about 1 in 10 of these mobilized systems actually make it to the surface to erupt. I need to introduce the concept of Caldera Volcanoes. I'm sure there's, I'm aware that someone talked about, Dave, I think, that talked about collapsed calderas in last week, but I just want to make sure that you have an understanding of calderas, because I'm going to be mentioning calderas quite a bit. So a caldera is really a large system, a large volcanic system, probably the largest volcanic systems that we know on our planet, where you have a magma chamber and vast amounts of magma are actually erupted. And as this magma chamber empties, we have a volcano tectonic event occurring whereby the crust, the roof rock here, actually falls into an emptying magma chamber. And what happens is that entire mountain chains are being sort of dumped into this emptying magma chamber, and what is left behind is a caldera depression, quite a substantial hole in the ground, if you want, where we have a caldera wall that could be anything from a few hundred meters to a few thousand meters tall. So the ground really sinks in, magma is being explosively removed from the magma chamber, but the roof rock here sinks into this emptying magma chamber because you're making room, you're making space, and the crust collapses into this reservoir. Okay, so that's the issue, or that's the concept behind collapsed calderas. Collapsed calderas are associated with the largest eruptions on our planet. Volumes of magma being erupted during caldera forming events are on the order of hundreds to thousands of cubic kilometers. So they are much bigger than frequently occurring eruptions that are perhaps of 1 cubic kilometer or less. So those ones are very rare events. They have return periods in the order of many tens of thousands, if not 100,000 years, okay? Whereas smaller scale volcanic eruptions have return periods of a couple of years. So these are really rare events, but if they happen, they have catastrophic consequences. I'm not sure whether people have talked about the issue of volcanic unrest and what it is. Well, I'm going to be showing you a couple of slides in a moment where I'm going to be demonstrating the geophysical fingerprint of volcanic unrest. But this picture here shows a satellite image of Italy, and Italy, as you know, hosts many volcanoes, some of which are actively erupting, such as Stromboli or Etna. They are, persistently active volcanic systems, but Italy also has volcanoes that erupt just every now and then, like Vesuvius, the last eruption about 70, 80 years ago. And then there's something called Campi Flegrei here, where we know that over the last 2,000 years we have had volcanic unrest. So there are some geophysical indicators that this volcanic system is still alive, but we've not really had substantial volcanic eruptions. In the case of Campi Flegrei, the last eruption was in the 16th century, but just in the recent 60 years or so, we've had more than 3.5 meters of vertical uplift in this caldera, that volcano, without any renewal of volcanic activity. So in this case, the Campi Flegrei, 400,000 people live within that volcano. So there's huge implications for volcanic risk, and with a population of 400,000, there's a real need to better understand the subsurface processes and their link with the potential renewal of eruptive activity. So this is what I've just explained earlier. The caldera would be around this size here. So this is the periphery of the caldera, around about 20 kilometers in diameter. It's about 400,000 people living inside this caldera, and this caldera has a number of smaller vents, with this one being the most recent one, erupted in 1538. Any volcanic eruption in this area, you can clearly see the number of buildings in here. Is a highly and densely populated area. Any volcanic eruption within this caldera complex will have a massive impact on the local population. People who have perhaps visited this area would recognize that this is the city of Naples, and Vesuvius would just be over there, very close to this system. Now, volcanic unrest is something that evolves over time. It's really hard to put a clear definition out there for what it is that we could term volcanic unrest, but usually it's either something where if you have a volcano observatory and staff members, they get nervous because some of the observations and some of the data they are collecting is unusual than normal, right? So volcanic unrest is really some sort of a deviation from the baseline or the background behavior of a volcano. And that can be expressed in different ways. So I'm showing you here some seismic signatures. So LP means long period events. VT are volcano tectonic events. So they start and evolve over, this is about 1.5 years before an eruption. This is an eruption in Central America, where the eruption occurred here, marked by this red line. And you got, weeks and weeks and months of anomalies. So seismicity, a thermal anomaly, seismic tremor, and then also followed by SO2, so sulfur dioxide emissions. And you can see in this timeline here, which is a way of more quantitative representation of those timelines here, that, for example, if you look at these LP events, they kind of follow, for many days. So this is October 4th to June 5. So this is 3/4 of a year. They do their thing, VT events and LP events. And then you somehow have a change in the system, and then things accelerate very quickly. Also here in the RSAM, which is the amount essentially of energy released by seismicity, you really have a ramp up towards the eruption. So all of that prelude here, you would now call them pre-eruptive processes, because of course you have an eruption, so you know that they are somewhat intimately linked with the eruption. So these are, you'd be more than welcome to term these events here as precursory. Now imagine if you hadn't had an eruption. That's also the case in many volcanoes, then it makes the interpretation of some of these data sets very difficult. Sometimes you have data or time gaps between significant unrest and eruption on the order of many years. And giving you the example of Rabol, perhaps, where in the 70s there was a very pronounced period of unrest with substantial ground deformation, earthquakes, and so forth. But the eruption didn't really happen until 1985. It's also, and this is a publication we produced back about 10 years ago now, so, 2013, where we looked at global unrest patterns. This is a volcano called Cotopaxi in Ecuador, and you see some of these unrest periods. They come off and on. They're not necessarily continuous. The next eruption here actually happened in 2005, whereas this is a protracted period of sort of intermittent unrest without leading to an eruption. And of course, if you work in a volcano observatory and you're being asked by the public or by politicians what it is that creates this process and what the likelihood of an eruption might be, then you're really hard pressed to use this information to come up with anything politicians might expect in terms of a binary answer. Is there going to be an eruption tomorrow? Yes or no. So it's a lot of pressure on the scientists trying to interpret these data sets. Looking at the statistics of unrest duration. So this is a statistical analysis we did as part of that paper. Most unrest durations are on the order of a couple of 100 days. So a mean value out there is on the order of about 3 months. But you can see there's a number of outliers, and these are not few, there's actually quite a few of them, where unrest duration could be on the order of many, many years, tens of years, if not even longer. I've mentioned Campi Flegrei. We know from analysis and records and historic records that the unrest there has been ongoing since Roman times. So there's evidence for more than 2,000 years of unrest at that volcano. So let's go into a really interesting study here, which is called a zombie volcano here. We're traveling to South America. This is Brazil. This is Chile. This is Argentina. This is Peru. This is Bolivia. And in the south of Bolivia, there's a volcano called Uchuruncú. And that's an interesting volcano. It's because that volcano technically is what we would call extinct. It hasn't had an eruption for more than 250,000 years. For a volcanologist, a volcano is active if there's evidence for activity for volcanic eruptions over the last 10,000 years. So by all means, that volcano should be extinct. It's not been doing anything for 250,000 years. It's built on an area where we have significant volcanic activity, but a long time ago, so 15,000 cubic kilometers of magma was produced in a period between 15 million years ago and 5 million years ago. And that formed this huge plateau. And then about 1 million years ago, this volcano started building and having eruptions up to about 250,000 years ago. So you might wonder, why is that volcano really interesting? Well, I mean, I'm mentioning here the zombie volcano because technically speaking, that volcano is dead. But this dead volcano really shows signs of subsurface activity. And we've been studying that activity for the last almost 15 years now. And what triggered this research was the recognition from satellite remote sensing that there's a large deformation anomaly in this area. By deformation anomaly, I mean that the ground is moving differently to the surrounding areas. And in this case, Uchuruncú is situated here in this sort of red blob. So these colors are INSAR data. So this is satellite remote sensing of ground movement. You can see here, this is millimeters per year. This is the rate of uplift in this red color here of about 6 millimeter a year. The interesting story there is that this volcano is surrounded by these blue colors. So there is a fringe, a moat of subsidence where the subsidence in this area is around 2 millimeters a year, but uplift is around 6 millimeters a year here in the center. So if you were to envisage this in 3D, it looks like a sombrero hat, a Mexican hat. It's also sometimes referred to as sombrero uplift because the periphery of that volcano is subsiding, but the center here is actually uplifting. You'll also notice that the volcano is here, but the area of uplift is much, much broader than the volcano itself. In fact, the volcano has a footprint of around here, but the area of uplift marked by these green, yellow, and red colors is on the order of about 80 kilometers across. So uplift is affecting a number of volcanoes there. So this is why we call it a zombie volcano, because it is uplifting, although really it should be dead for the last 250,000 years. Now, seismically, people have been, so this is a study by Ward that was published in 2014, seismically using shear wave velocity data and converting that into a tomography. they were able to show that this entire region is underlain by a large body of partial melt, which is called the Altiplano Puna magma body, abbreviated APMB. So this is about a 200 kilometer wide, probably 10 kilometer thick zone of partial melt. I mean, you don't imagine this is a pool of liquid rock. There's partial melt in there, but not everything is molten, okay? It's probably what we would call a mush. Parts of it is crystalline, but there is evidence for some of that being partially molten, okay? And many of these volcanoes that are shown here, these are hundreds of volcanoes, they seem to be fed somehow by magma generated at this APMB. The question is now, what is the link between uplift in this part of the Altiplano Puna region at around Uchirunku and the APMB? Now, if you look at the seismic pattern, look, seismicity is reported here, 2009, 2012, where we've installed a seismic network to look at seismicity, and you see that this volcano is surprisingly seismically active. And most of the seismicity is actually occurs around about sea level. So the volcano is 6,000 meters high above sea level, but most of the activity here is concentrated around sea level. So if you were to put a seismic brittle ductile transition, you will probably have something like this, right? So there's probably some sort of a 3D geometry behind this. And if you use the data, and you look at the B values, and I'm sure that in other seismic studies, B values are really important, but in volcanology, they're hugely important because they tell us something about the processes behind the seismicity. And there's two different studies being conducted on exactly the same data set, but it may be interesting for the seismologists amongst you that you get drastically different B values depending on whether you use the local magnitude scale or the moment magnitude scale. The local magnitude scale we would infer a B value of 0.8, and for a long time this has really been puzzling us because that would indicate that this is a really dry system without many fluids, whereas all the other indications we had from a ton of other observations, we always thought there's a lot of fluids, magmatic fluids, being pumped through the system. So a B value of 0.8 derived from a seismicity, it didn't really make sense for all the other people that worked on other aspects of those sort of processes. Now, Tom Hudson, who is the lead author of that paper, he recalculated or reanalyzed the catalog and calculated moment magnitudes, and then provided the B value fit. And a B value fit of 1.44 was derived from this data set, which makes a lot more sense in terms of this entire system being really wet and being dominated seismically by processes underpinned by fluid flow through the crust. Please be reminded that the crust here is incredibly thick, similar to Tibet, for example, in the Himalayas. We're looking at a crustal thickness here of around 75 to 80 kilometers. This is an incredibly thick crust. Now, if you look at the deformation, I've already mentioned it earlier, these are different satellite remote sensing images, or tracks as we call them, where sort of an average maximum uplift rate around Uchirunku is on the order of 0.8 to 1 centimeter a year. Now the question of course is, how long has this deformation been ongoing? And from satellite geodesy, we've got coverage of about the last around about 25 years. Geomorphology studies indicate that there isn't really any tilting, any remnant or residual tilting of this entire area, meaning that whatever is driving, it can't really be more than a few hundred years, because you would then have the fingerprint, if you wish, some sort of evidence in the geomorphology, such as lake beds being inclined and stuff like that. So we're kind of in the sort of the uncertainty behind a couple of tens of years and maybe a couple of hundred years. So what we've been lucky enough to being able to reoccupy a leveling line that the Bolivian military undertook and measured in the 1960s. They undertook leveling measurements in 1965, and what we did is we went back and reoccupied the leveling line using GPS and also gravimeters, and trying to figure out whether we can actually identify any changes in the elevation in between 1965 and when we conducted the study. That was in early 2013 and 2014. And if we could identify any ground deformation, is that in line with the deformation that we could see from satellite imagery? Again, this is the satellite imagery. This is shown here, the red being uplift and the blue being ground subsidence. So the ground being down warped and this one being uplifted here. Okay, so and you can see that we got a pretty good coverage in the area where we have INSAR data. Now, to cut a long story short, we were able to correlate the two data sets through a geomatics approach. And what we are able to show is that indeed the deformation that we see from INSAR is comparable to the deformation that we could constrain from comparing the 1965 benchmark elevations with the ones that we were able to derive in 2013-14. So broadly speaking, we have an area of uplift, but we also see an area of ground subsidence. And perhaps surprisingly, that if you go back in time, back to 1965, the area that is subsiding is actually much more pronounced in amplitude than what is retrievable by INSAR. So we're probably having 2 or 3 times more subsidence, more ground subsidence than what was tracked from 1990 onwards. So that's really interesting in terms of trying to understand what is actually driving that process, or what's the driving process behind this ground uplift. So what we could infer from our study that we are dealing with at least around about 55 years of ground deformation. Ground deformation is still ongoing, although it's been slightly muted, and we've dropped the maximum ground velocity from about 0.8 to 10 millimeters, from 8 to 10 millimeters a year to round about 2.5 to 3 millimeters over the last 5 or 6 years. So the ground is not uplifting at the same rate as it used to, perhaps 25 years ago. When we look at other geophysical information, and this is gravity data that we collected over the years, and I'm going to show you examples from two inversions, so gravity inversion using Boogie anomaly data. We can actually, first of all, we can perfectly image the APMB, so the magma body, but what we can see is that we have vertically extensive, let's call them connections, just I'm using a very neutral term now, vertical connections between the magma body and the surface. Now, this study was done at, in between 2010 and 2012, and the paper came out in 2013, where we put in where we occupied 5,000 square kilometers of new gravity measurements. But because of the spacing of the gravity stations, we only had real confidence of those inversions up to about sea level. So a couple of years ago, I went back to collect more data, and this is now shown in this one, where we have a much coarser, a much finer sort of density grid or station grid around Uchurunku itself, and we could then invert the data to show what is actually happening 5 kilometers between, let's say, sea level and the surface. And what you can see, and this is from a 3D inversion and an animation, we're looking down, we're looking upwards from beneath up towards the surface, and we can see that these bodies are well connected, and they actually branch out at the upper crust, so above sea level, and seem to connect to with the volcanoes up there. So this really gives you the impression of a well-connected transcrustal plumbing system beneath those volcanoes in the Altiplano Puna region, a transcrustal plumbing system that I've introduced in the second slide, where we have different the different compartments in a way of magmatic magma chambers and other reservoirs that connect a large magma reservoir to the surface. So that study just came out very recently, just a couple of weeks ago, and you can, if you wanted, you can sort of have a look at that. We can also see vertically extensive anomalies in the magnetotelluric data, where we see different resistivity profiles here, two of them, and clearly we have very low resistivities in parts of that volcano at different depths, very close related to the depths of the density anomalies that we've highlighted in the previous slide. So some of these resistivities are really low. So these are huge conductors, probably to do with the translation on the ascent of fluids from the magma reservoir down here, the APMB, towards the surface. I'm not going to be dwelling on this one other than to show that this is really important in terms of trying to understand what we know about the system by now. We know a lot from petrology, from geophysics and so forth, and thermal studies. So this is a slide that is far too busy to understand. But this is really to show you that we know quite a bit about the system now. And hence we are able to inform numerical models. And one attempt I've made a couple of years ago, trying to put all the information that we know about the system into a numerical model, a thermomechanical numerical model, to see whether we can explain both the ground deformation and also changes in the gravitational field of that volcano by the processes that we've been hypothesizing. And I'm not going to be dwelling on this, but this model is able to reproduce the deformation quite well. So these are different fits to the data. The observations are in red, and we can explain this by two different models, whereby we think magma is being channeled towards the surface, either just as magma or in terms of a hybrid where we have magma at depth, but fluids being released from the magma and traveling towards the surface. The model can't really differentiate between the two possibilities, a hybrid source, so magma plus fluids, or just magma. Okay, so this is the uncertainty behind this model, but it seems to be evidence for partial melt moving from the APMB towards the surface, where it interacts with a colder upper crust. This is where the seismicity is located, because we're bleeding fluids, and the seismicity at that depth is in line with where petrological models would predict that the fluids separate into a liquid and a vapor phase, and because the vapor phase needs far more space, so you have a volume increase. In order to create the volume increase and accommodate the vapor, you need to fracture rock. And this is what's happening here. So most of that seismicity is probably associated with hydrothermal processes. Okay? So we need to infer an active hydrothermal system behind that volcano, and we have active fumaroles on that volcano. But this is really a large-scale transcrustal process underpinning the large and widespread deformation anomaly in that part of the world. I want to go briefly into introducing the main Ethiopian rift. This is a beautiful picture here from giving you the landscape of the main Ethiopian rift. At the eastern part of Africa, this is the Horn of Africa. Ethiopia is here. So this again, we zoom into that area, the Afar depression, and a number of magmatic systems underpinning this continental rifting zone. If you look at, again, INSAR data, this is a paper from a colleague of mine who's looked at different volcanoes, and she found that many of these volcanoes actively undergo ground deformation. Many of these volcanoes have not erupted in a long period of time, thousands of years, so there's not really a real recognition that volcanic eruptions may be a problem in this part of the world. But they show huge signs of deformation. The question, of course, is, are these deformations indicators for future volcanic activity, or is that just to do with hydrothermal processes? So volcanoes, how volcanoes breathe, they breathe in, they breathe out, and this is really nothing to worry about? Or are these really indicators that we're building up new magma reservoirs at depth? I'm going to be showing you an example from Corbeti. Corbeti is again a caldera. You can nicely see here in this digital elevation model this large size of this caldera. It's about 20 kilometers across. And in the center of this volcano, two new volcanoes have grown. That volcano, the caldera itself is really old, maybe about more than 1 million years, but these are quite young, with eruptive return periods of around about 1,000 years. So, but we haven't seen any eruption there for many thousand years, but from petrological studies and dating, chronological dating, we can tell that eruptions occurred around about with return periods of around about 1,000 years. I'm moving on. I'm sorry. Let's go back. There's a student of ours has done some models to explain the ground deformation, and it could either be some sort of what is called here a point source or a cell model. So that this is a horizontally extensive one, and this is just a point source. So equally, the data could be fit with the two data sets. But of course, if you only look at ground deformation, you don't really have any information about the nature of the source that's driving the ground deformation, whether it's, for example, magma, or whether it's aqueous fluids or hydrothermal fluids. So this is where gravity comes in. We've been collecting gravity data in that part of the world. It's really difficult to create it, to collect it, because it's really hard to access and to work in this part of the world. But what we've been able to do is we were able to gather some data over a number of years that show that gravity is really increasing as you go closer to the center of uplift. And this is called residual gravity. So this gravity change is already corrected for the effect of ground deformation. So in other words, in the ground, there must be density must be increasing there to some level. And again, if you put everything into a thermomechanical model and you inform this with data that you can infer from seismic studies, for example, to construct a mechanical profile and a density profile through that volcano, you can see that this model can adequately explain the ground deformation data. So these are fits to the observations. They are absolutely acceptable to capture the first order dynamics beneath that volcano. And what we think is happening there, and I'm showing you this, is that we've got a magma reservoir that is being replenished. If you interrogate the data, this is a very busy graph, but you can really interrogate both the geodetic data set and the gravimetric data set to infer some processes within the magma reservoir, such as a likelihood of reservoir compressibility, what kind of annual reservoir density change the system is undergoing, and what's the pressure change. So you can really use the multi-parameter data set to learn something about the processes driving ground deformation at that volcano. To cut a long story short, I'm going to show you this summary sketch there. So what we are thinking and what the data show is that actively there's an active growth of a shallow seated magma reservoir. It's being fed from depth, and we're probably assembling a shallow intrusive complex there beneath that caldera. The interesting part is that the source depth and also the source density are in line with petrological studies of past eruptions that fed those two stratovolcanoes that are located within the caldera complex. So there's every indication that the system there is still active, despite there not being an eruption for the last 1,000 years. And it may be that this shallow intrusive complex may feed volcanic eruptions there in the future. This has, of course, implications for hazard and risk assessment in this very densely populated and area of the main Ethiopian rift. And these are sort of findings that could then be taken aboard for more detailed studies on risk and how to mitigate risks. So last not least, and I'm going to be finishing soon, is the example of volcano tectonics. I'm going to be talking about two examples, one from El Salvador called the Ilopango caldera, and the other one's from Turkey, from Hasan Dag volcano. This picture shows a caldera lake that's filled in a large caldera at Ilopango in El Salvador. And we've been able to look at this system a couple of years ago. So the volcano tectonics are really interesting here. This is Ilopango caldera. It's one of a series of large calderas stretching all across from El Salvador into Guatemala, large magmatic systems, large volcanic systems, being somehow associated with a large pull-apart basin here. Textural strike slip system and with some degree of extension, and this probably has some effect in actually mobilizing magma, generating and mobilizing magma from depth. If we zoom in, the study area here was very close to San Salvador. This is the capital, a couple of million people living here right at the outskirts of this large caldera. So again, there's substantial implications in terms of hazard and risk. And you can see that there's inference of that caldera being somehow associated with this main strike slip system that crosses the entire length of El Salvador. Now we've done gravity measurements, new gravity measurements to construct a new local anomaly, Boogie anomaly map, and you can clearly see the outline here of the caldera lake. And these are mapped faults from published papers. You can also see there's an alignment of younger volcanic, we call them domes, eruptive vents. And the structure of this low density anomaly here, expressed by the local gravity anomaly and negative anomaly of around about 20 milligauss from the surrounding area. So this indicates that there's low density material at depth. And I think you can appreciate just qualitatively that there seems to be a link with those structures and the shape of this anomaly. Now, if you look in greater detail, for example, what I'm plotting here is the horizontal gradient of the Boogie anomaly. Again, we've got these mapped lineaments and fractures and faults, and they are really highlighted also in this gradient analysis. So what you're looking at are these bright colors. They show lineaments that are in line with the existing and mapped structures. Now, if you don't believe that, you think this is all just fake, and you can actually see this in a statistical analysis where we have the extent, this extent and that extent of the anomaly correlating with major trending fault systems, one being northwest, southeast, and east-west, and the other one at more or less right angle. So this is clearly expressed by the density anomaly. If we run the inversion and animate the negative anomaly here for a 200 kilograms or negative 200 kilograms per cubic meter density contrast, what we believe is in line with a magmatic plumbing system. So this is what the 3D representation of that plumbing system might indicate. So the plumbing system actually nowadays extends beyond the caldera wall, and it feeds lava domes in the north up here. So this is a way to sort of try to imagine what this magmatic system looks like at that volcano. Last but not least, I've got 3 minutes more to go, and then I'm going to be finished. This is a volcano called Hasan Dag, a large towering volcano, almost 3,500 meters high above the central Anatolian plateau, not too far away from a major city called Aksaray, about 1 million people living there nowadays. large pyroclastic flows that come down that volcano in the past. But again, it's not been showing any activity in the living memory of the population here. There is indication that this volcano might have been active or was active about 5,000 or 6,000 years ago, likely associated with the most recent large-scale tectonic event in this area. So the volcano is at the intersection of two major tectonic systems, one striking northwest southeast and another one at right angle to that one. This one is much better constrained than that one over here. This is really only sort of shown as a sort of broken line. Here, the fault system is really nicely mapped and nicely, really well studied. So we know that we've had with about 5,000 years of return time, two major seismic events. If you then calculate the documented aseismic slip on that northwest southeast trending segment of that strike slip system, we think there's a potential for a magnitude 5.9 to about 6.8 earthquake. Now, the key question we've been having is, okay, if this is the next sort of, if that's the order of magnitude for the next earthquake, what be the implications for the magmatic system here? You know, that volcano has an active hydrothermal system. Fumaroles are very close to boiling temperatures, around about 80 or 90 degrees at that altitude. This is close to boiling. So the question really becomes, you know, what's the stress transfer between, let's say, a seismic event and this magmatic system? In other words, could tectonic event trigger a volcanic eruption there, or the ascent of magma from depth? So we've constructed a model here. I'm going back here. It takes into account the mechanical layering in this area as from seismic studies and so forth. It's a full 3D model, has topography and everything. And this is the major fault that's shown here, trending northwest southeast, as I said earlier. We have used any information that we have from magmatic telluri and also from meteorological study about the depth and likely size of that reservoir. And what we've been testing is how would stress transfer in between those two systems, the tectonic system and the magmatic system, sort of play out in terms of a possible rejuvenation of volcanic activity in this area. And we've tested different right lateral slip and normal dip slip motions. So this is for one example here. We're doing a Coulomb stress analysis of failure stresses for different orientations of feeder dikes emanating from the top of this magmatic system to the surface. So for what we can see, the blue colors and red colors is the Coulomb stress change. The blue colors are those that have been accumulating prior to a seismic event due to the aseismic slip. And the red colors indicate the Coulomb stress changes caused by a future earthquake of the magnitudes of the magnitude range that I have described, in between around about 6 and 6.8. So for any systems that strike perpendicular to the major fault systems, we can actually see negative stress changes here, that the system is probably locked in that direction. However, the system is in a completely different state if we look at areas that are striking parallel to the major fault zone here. Even by just looking at the aseismic slip that has occurred at that system, those faults, for example, they've been unlocked. They've been, you know, continually being unlocked, and then if you add another earthquake, you would have additional unlocking or unclamping of these faults, with the possibility of real stress transfer from the tectonic system to the magmatic system, such that there may be a higher probability of unlocking faults and conduits or feeder dikes that are oriented along the strike of this fault zone compared to those that are actually not aligned. We've tested our model predictions Fortunately, we've had an earthquake, a magnitude M5 earthquake back in 2020. On this sort of secondary fault zone, the model will predict that this area would undergo unclamping because of the aseismic slip along this lineament here. And so our model, I think it's fair to say, accurately predicts unclamping in that area. So the earthquake occurred in an area where we would actually have predicted unclamping of faults along this strike of this fault zone. So I'm going to be ending now with a summary. So I think I've been able to show you the different flavors of volcano unrest, manifestations of complex subsurface processes. I've given you different flavors, one to do with fluid migration through a large transcrustal magmatic system. In the case of Bolivia, that zombie volcano that should be dead but isn't. In the context of Ethiopia, I think we've shown that there's magma being fluxed into a shallow magma chamber, contributing to perhaps a higher probability of eruptive renewal in the future. In El Salvador and also in Turkey, we've seen a really clear tectonic, volcano tectonic linkage where tectonics control, first of all, caldera formation and also the extent and orientation and geometry of the magmatic plumbing system. And then in Turkey, we could demonstrate that the tectonics either contribute to clamping or unclamping of magma pathways, where there is a good chance of the future major seismic event having the potential to really open new pathways for magma to move from the magma chamber towards the surface. Whether this is going to end up in a volcanic eruption, of course, it's really hard to tell, but there's ample opportunity for this magma reservoir to fail and send magma, from the reservoir towards the surface. So again, volcano unrest is a really interesting scenario to study. There's really a lot of complex subsurface processes, and disentangling these processes is really, really challenging. I think, or hopefully I've been able to show you that the multi-parameter aspects of using seismology, using volcanology, geodesy, magnetotellurics, using geochemistry, all these different flavors of trying to understand those systems better are really needed. All these different ingredients are really needed in order to study those processes in great detail and hopefully be able to disentangle the contributors and isolate magmatic from tectonic and hydrothermal contributors. This, of course, has major implications for hazard and risk assessment in these areas, because magma movement is something different to hydrothermal movement in terms of volcanic risk. Those studies that we've been conducting are, of course, sort of focused on the investigation of magmatic systems, but many of these studies, many of the tools that we use can be equally applied to, for example, studying reservoirs to do with oil and gas, CO2 sequestration, and so forth. So it's only that, my focus is very much on volcanoes, but many of these tools can, of course, be equally applied to the study of other reservoirs. So I'm going to be ending here. Thanking you very much for your patience and sticking with me. It's taken a little bit longer than I anticipated, and I'm looking forward to fielding your questions. I'm putting a couple of papers here together if you needed those for further reading. I'm happy to share this presentation with you, of course, should you wish so. And I'm again thanking you, and I'm taking your questions now.
Okay. Thank you, Professor Gottsmann. Thank you for such a interesting and insightful presentation. Your lecture really will be really helpful to understand the subsurface processes that is responsible for the volcanic activities and formation of volcanoes. Now, I would like to request our session chairman, Professor Kyle, sir, for his final comments. Over to you, sir.
Thank you, Chinmay. Thank you. Congratulations, Professor Grossman. It was a wonderful presentation, and we really are enlightened with your vast experience and knowledge on volcanology. You have explained so elaborately about the ground deformation, then the volcanic and tectonic activity relations. So all those were very well explained and well illustrated. And long back, I visited Bristol University in UK sometime in 1995. And if I remember, you have also got a very good group in GPS and seismology, microscopic seismology. I'm just wondering whether there is any effort has been made for, say, prediction of volcanism for an active volcano. Means you have given very good examples of how a larger earthquake can trigger volcano, but I am just wondering whether you have any efforts, any work has been done by monitoring microseismicity to predict exact time of the volcano, which is possibly possible. Your comments, please.
Yeah, I've got a comment on that. So when monitoring active volcanic systems, and those that are really not zombie volcanoes, but that have eruptions, seismic studies are one key contributor to forecasting. And there's all sorts of different forecasting tools available, a failure forecast and so forth. There's different softwares available, and it's kind of it's down to the different observatories which tools to use. So I'm tempted to say there's sort of three key contributors to forecasting eruptions. One is seismicity. The other one is ground deformation, but also gas emissions and changes. But what we're really looking at is what I said earlier is deviations from the background activity, right? So, and that's sometimes really hard to do because in order to use those data streams, you need to have really good networks of instrumentation. And not all volcanoes, very few volcanoes are actually instrumented to a degree where you can reliably use the data streams to forecast. But even if you did, allow me to go back to a classic example, which I showed you earlier. Just look at the evolution in terms of just the seismic fingerprint here. I'm gonna put this on here a little bit bigger, a bit bigger here.
Yes.
So let me show you. Where's this now? So come on, yeah. Look at that. So let's say RSAM. That's a really good indicator.
That's right.
But you see that it's increasing. I mean, this yellow star here is the first what we would call phreatic eruption. That's just hot water. The red line is the volcanic eruption, right?
Yes.
And this is August 5 and this is October 5. So this is 2 months. The acceleration here, you see, the acceleration would perhaps, most people would predict the eruption to occur around about the beginning of September.
Yes.
You see?
Yeah.
But the RSAM actually tails off at the timing. The eruption actually occurs when the RSAM is already on the way back. You see, and this is one of the key problems people have been having with trying to sort of figure out that the fastest acceleration. That's really the key. Where this is the greatest likelihood of this eruption to occur.
Yes.
So RSAM completely misses the onset of phreatic activity, right? And also probably preempts the indication of the magmatic eruption by at least a month. And that's the uncertainty behind using forecasting methods based on these observations, right? Now, it may be that, if you got a really great network and a lot of experience and having, a lot of data followed by loads of eruptions, So if you had pre-eruptive sequences for 10 different eruptions, I think you can really, I'm tempted to say you can really inform your probabilistic forecasts better because you constrain some parameter better than the other one. But most volcanoes have eruptions that are completely out of the blue, right? Take the example of La Palma, for example. The last eruption there was in the 70s. It's erupting as we speak now, right? But in the 70s, there's been very, very poor geophysical or any scientific underpinning of the pre-eruptive processes. And really the eruption that happened or started a couple of weeks ago really only had about 1 week of anomalous seismic activity, right? So it's really, really hard to interrogate pre-eruptive geophysical data sets for accurate forecasting if you don't have numerous sequences of very well instrumented pre-eruptive episodes leading to eruption.
Thank you so much. Thank you. Well, very well explained.
Yeah,
Thank you so much. Thank you.
Yeah.
Over to Chinmay, I think. Over to Chinmay for his anchoring. Yeah.
Thank you, sir. Thank you, Professor. Now may I request our session co-chairman, Dr. Saurabh Barua, sir, for his comments. Over to Barua, sir.
Yes, good evening, everyone. Professor Joachim Gottsmann, it's a really wonderful lecture, and it's an eye-opening for all of us who is working on this kind of geodynamics of northeastern region of India. So, as you have rightly said, that the same technique can be applied to carbon sequestration, gas-filled areas. It is well taken care of. I think we really can adopt these techniques to those fields, which is a new enhanced idea for us. Once again, thank you very much for your excellent deliberations. And I hand over the mic to Dr. Chinmay Rajkumar.
Thank you, sir.
Thank you.
Now, with your permission, sir, can we take some queries from the participants? Shall we proceed, sir? Yeah, thank you. So may I request Prachurya Barthakur to conduct the Q&A session?
Thank you, Chinmay sir. Namaskar, Professor Gottsmann, sir. Thank you so much for such an astronomical talk. Now, for your assistance, I am going to read out the questions from the participants across the globe. And the first question is, could we be able to exploit all the energies of active magma chamber before eruption for renewable energy source and saving the area with geothermal hazard?
So I'm not entirely sure I fully understood the question, but it's about geothermal energy that is, and geothermal reservoirs that are fed by magmatic systems.
Yes, sir.
Is that correct?
Yes, sir. And the energies of the active magma chamber before eruption could be used for renewable energies.
I see. Okay. Yeah. I mean, there's an intimate link between geothermal reservoirs and magmatic systems. There are, of course, many geothermal systems that are linked to tectonics, but most systems that are actively exploited are to do with volcanic or magmatic systems. And calderas play a very important role here. I want to keep my answer really short, but most of the most powerful geothermal plants worldwide, whether you go to New Zealand, you go to Central America, you go to Iceland, you go to other places, they are all harnessing the energy that is stored within geothermal systems, powered and replenished by magmatic systems. there's a huge drive, for example, nowadays in East Africa to harness green energy from geothermal power plants. Corbeti, for example, Corbeti has had $4 million of investment to build a brand new power plant to harness the geothermal energy stored within that system. Now you can imagine if the research that we conducted at Corbeti was very interesting for those people who've been trying to fund the construction of a power plant there, because it's not entirely clear whether, as you recharge the magmatic system, whether that's good or bad for production, right? So there's huge financial implications, financial risk that needs to be assessed. So there's a clear link between those that operate and want to invest in geothermal energy and those who do research along the lines that I'm doing research. So there's an exchange, of course, of ideas and also of knowledge, because they absolutely rely on trying to get a better understanding of how these geothermal systems actually work, right? Now, I guess my other point is that calderas are hugely important for the provision of geothermal energy because they are long-standing magmatic systems. So many of these systems have been operating for many hundreds of thousands, if not millions of years. So the crust is hot. Even if the volcano has magmatically died, the thermal fingerprint is still with us for a long, long time. And that's really all that is needed in order to maintain a state of the geothermal reservoir to be exploitable. Let's put it that way. So I hope this answers your question.
Thank you, sir. The next question is, as you all know that most of the volcanoes are present in the boundaries of tectonic plates, and few are found in the interior plate due to hotspot activities. But why there is no active volcanoes in the Himalayan and Indo-Burma arc region? What could be the reason? Does the thickness of the Earth's crust plays an important role in the eruption?
That's really interesting. It's a really interesting question, because I mentioned that the Himalayas and then Tibet, you know, have a very similar crustal thickness to the Andes, where I've been sort of using the zombie volcano example, right? The key story there is it's a subduction zone in South America, and you can very clearly. I should have. I mean, I couldn't show everything we know about the system, but the study that Tom Hudson did, and in terms of the seismicity, you can clearly show that fluids actually are derived from the subducting slab, and they make their way all through the mantle, through the thick crust up to the surface. So, and you need fluids, aqueous fluids, so you need water that's being released from the subducting slab in order to partially melt the crust. If you're not doing that, then you have fewer amounts of, lower amounts of partial melting of the crust. And if you don't melt the crust, you can't actually get to the silicic contribution, the silicic composition that is needed to sustain large-scale volcanism. Large-scale volcanism and many calderas, that you need rhyolites. The rhyolites are essentially a product of melting the crust. You can only really melt, if you look at phase diagrams, you can really only melt the crust if you provide it with substantial amounts of fluids. Right, this lowers the solidus, and you can then start melting the crust, form crustal melts, and then make it to the surface to erupt. Without that, it's kind of difficult. So I guess I've never worked in the Himalayas. I should really visit that part of the world one day, but I've never really worked there scientifically. So I would say, because this is a collision zone, we don't really see. So it's compressional tectonics. We don't really see the amount of fluids being churned through or pumped through that system as we see it in the Andes. The area in the Andes, we've also seen we've studied, you can also see the tectonics associated with strike slip, but a slight extension. So there's extensional tectonics that have probably contributed to the large scale volcanism that I described between 15 million and 5 million years ago, because you somehow need to accommodate vast amounts of magma in the shallow crust. So probably extensional tectonics there. You could call it the back arc. It's not really entirely clear what the seismic, what the tectonic relationship there is, but there's some degree of interaction between a subduction zone and local areas of extension in generating the space to accommodate these large amounts of magma. So hopefully this answers the question.
Yes, sir. Yes. So the last question is, what is the significance of interplay volcanism? How does it happen?
Okay, that's a really interesting question. Again, I mean, intraplate volcanism is huge, usually in I hope I'm not sort of on thin ice here. It's almost exclusively, I'm tempted to say, associated with crustal extension. There's some degree of rifting, whether active or past, but what you need to have is a degree of mantle upwelling that then feeds volcanism. In many places, intraplate volcanism is exclusively mafic, so you could perhaps get nephelonites, basanites, maybe some basalts. So essentially, this is those magmas are a clear product of mantle upwelling. But there are some places, if you go, for example, to the East African Rift or Iceland, where you also have crustal melting, where you generate not just the mafic magmas, but also highly evolved magmas. I've not mentioned the name, but in the Ethiopian Rift, you have a lot of examples of peralkaline rhyolites. These are really high in alkalis, so potassium and sodium. They're hugely, these magmas are very fluid, although being of a very high SiO2, so silica content. But these are processes that are kind of unique to some specific intraplate setting. And most of these settings are underpinned by plumes. So you go to the East African Rift, you go to Iceland, there's ample evidence for substantial magma generation and heat generation from not just transcrustal, but actually through the mantle as well. Some processes that give rise to mantle plumes that then interact with the crust. Without that, without rifting and without a magma plume, I don't think you can sustain volcanism very efficiently in intraplate settings. So again, it's down to tectonics, and then again, it's a chicken and egg problem. What comes first? Does the plume come first, or does the tectonics come first? So that's something that people are really interested in finding out. But it seems to me that you need both the tectonics and a heat source to sustain intraplate volcanism for a long time.
Thank you so much, sir, for your valuable answers. Due to the time constraint, we could not take further questions. Do feel free to answer them via email. Thank you, sir. Over to Dr. Chindu.
Thank you. Of course. Thank you.
Yeah, thank you, Prasidya, and thank you, Professor Gottsmann, for your response to the queries. So now we have come to the end of the session. So now may I request Mr. Nabojit offer the vote of thanks.
Thank you, sir. Thank you, sir. Namaskar. A warm good evening to one and all from the land of Red River and Blue Hills. As all good things come to an end in life, so is today's session. On behalf of the entire CSR News family and organizing committee of IBWGST 2021, I take this opportunity to propose vote of thanks to our keynote speaker of today's online meet, Professor Joachim H. Gottsmann, from University of Bristol, UK, for readily accepting our invitation and delivering such a nice and informative talk on the topic, New Insights on the Inner Working of Volcanoes. Sir, you have really enlightened us with your vast knowledge in the field of volcanology. We are very fortunate to have you among us in today's session. Once again, a hearty thanks to you, sir. Furthermore, our deep sense of gratitude and thanks go to Honorable Director of CSR in his Zohat, Dr. G. Narahari Sastry, for his moral support and its ubiquitous help in conducting IBWJC 2021. A hearty regards to you, sir. I feel fortunate to profoundly extend our gratitude to the international advisor of this workshop, Professor Andy J. Michael from USGS USA, and session advisor Professor Daping Zhao from Tohoku University, Japan, for their unflinching support and coordination throughout this workshop. I would also like to thank the session chairperson, Professor J.R. Kyle, former Deputy Director General of GSI, and session's co-chairperson, Dr. Sor Borwa, Chief Scientist of CSIR NIST, for their diligent commitment towards the event and providing needful guidance. I also extend my deep sense of appreciation and gratitude to Dr. Santanu Borwa, the convener of this workshop, for conceptualizing such a splendid idea to organize this virtual workshop and thus facilitate the direct access of geoscientific community with the experts and pioneers in seismology, tectonics, volcanology from across the globe. A special thanks to all the members of Technical Committee and Organizing Committee for their enormous support, dedication, teamwork, and persistent effort in successfully organizing this event. Last but foremost, I express my deep sense of appreciation to all the attendees for their active involvement and cooperation in today's event, without which this event would not have been a success. We also fervently desire your gracious presence in the next and final session of this international virtual workshop, which will go live at 10 AM tomorrow. Our keynote speaker for tomorrow's session is Dr. Sarah E. Minchin from USGS USA with her lecture on Shaking is Almost Always a Surprise, the earthquake that produced significant ground motion. With this, I conclude this session with hearty regards and anticipation. Once again, thank you all for being with us and making this event a great success. Namaskar or dhanyabad. Thank you all.
Thank you.
Thank you very much.
Thank you.
Thank you, Professor Gottsmann. Thank you.